Okay, today, this is the last bit of our permutations and combinations thing. It's just kind of an interesting concept that, I mean, it seems to be obvious in a way, but you can actually use it to find solutions to things. So, the pigeonhole principle is what it's called, and because you think about pigeons, for example. So suppose you have 8 pigeons and 7 holes to place them in. All right, so here's our, oops, let me turn the thing on. Here's my pigeons. That's not very good, is it? So here's my pigeons. I got 1, 2, 3, 4, 5, 6, 7, 8 of them. And I've got 7 holes. There's 6 holes. Then we've got 7 holes to put them in. So I could stick them in, don't have to stick them in one in every hole, but you could potentially stick one in every hole. But could you stick one in every hole? Potentially. Well, you couldn't, could you? Because you only got 7 holes. So once you put 1, 2, 3, 4, 5, 6, 7 pigeons in, then your poor old last pigeon that you haven't put in needs to go somewhere. So wherever you put that last pigeon, you're going to have two pigeons in it. Now you notice it says intuitively one of those holes must have at least 2 pigeons in it. And the reason for that is that, say you didn't initially put 1 pigeon in every hole, right? So say initially you decided for some reason that you were going to stick 2 pigeons in that hole. Well, then when you get to number 80, you can either stick him in a hole by himself, or you can stick him in another hole here, and then you've got, it says intuitive, one of the holes must have at least, well, it should, which it does. We've got 2. But if I didn't put him in there, and say I put him in here, then this hole has 3. So it's saying at least 2. All right, so all that last bit of waffle is, if you've got 8 pigeons, you've got 7 holes, you can stick 7 of them in a hole by themselves until you put that last one in, and then one of the holes has got to have at least 2 in it. All right, so how are we going to write this in terms of, so if n plus 1 or more objects are to be placed in n holes, then some hole contains at least 2 objects, and that's what here. So up here, n was 7, n plus 1 is 8, 8 pigeons in 7 holes. One of those holes had at least 2 pigeons in it. And so we can use this to solve problems. So here's an example. We have 13 red, 10 blue, and 8 green socks. How many need to be selected at random to ensure a matching pair? So the word ensure is the key one there, because you may pick the first 2 and you may get a matching pair bang straight away, but you might not. So we want to know for sure to get a matching pair, what do we need? Well, we've only got 3 options. We've got red, we've got blue, and we've got green. So if I've got a red sock, a blue sock, and a green sock out, n equals 3. So if I've got n plus 1, or in this case a lot more than n plus 1, the next one that I put in, one of those 3 holes has got to have 2 in it. All right, so to ensure at least 2 in any hole, we've got to go n plus 1. And so if n equals 3, n plus 1 is 3 plus 1, which is 4. So how many do we need to ensure getting a matching pair? We need to select 4 socks to ensure that we're getting a matching pair. On that 4th sock, if we haven't already got a matching pair on that 4th sock, we're definitely going to get a matching pair. Makes sense, doesn't it? All right, and so that's what the pigeonhole principle is kind of about. Here we go. So here we've got 7 teams playing a season consisting of 22 games. Show that some pair plays each other twice. All right, so what do we got? We've got 7 teams. For a game, what do you need? 2 teams. All right. Now, a game in this saying playing, some pair plays each other twice. So we're looking at Storm plays the Raiders is the same as the Raiders playing the Storm. All right. The same, the order is not important. So this is a combination. So for each team to play each other team once, from the 7 teams, we need to choose 2. How many different ways that we could do? That is 21. So we need 21 games for each team to play every other team once. They're the different combinations. So 21 games needed. But we have 22. So therefore, some pair play twice. Simple as that. There's just one more game. All right. Pigeonhole principle. All right, that's what that's all about. Let's have a look at another one. 16 natural numbers. Now remember, natural numbers, the word there, natural. Remember the natural numbers, the counting numbers, 1, 2, 3, 4, 5, 6, and so on. They're the natural numbers. Are written on the board. 16. Prove that at least 4 numbers will have the same remainder when divided by 5. All right, so how are we going to figure that? So the thing that we're talking about is the remainder. So it's the same remainder, okay? So the things we're talking about is a remainder. So what I'm going to do is we're going to create a pigeonhole. I'm going to create a pigeonhole for the remainder. So this pigeonhole here is if it goes in evenly and there's no remainder. This one is if there's 1 remainder. This one here is if there's 2. This one here is if there's 3. This one here is if there's 4. And 5 remainder, well, there can't be 5 remainder because it's being divided by 5. So that'll go in evenly. So what do we got here? We've got 1, 2, 3, 4, 5. So we've got 5 holes. All right, so that so we've got 16 natural numbers are written on the board. So we've got 5 holes, 16 numbers, and 5 holes to stick them in. Now, 16 numbers and 5 holes. So if I, for example, had 3 holes in each, 3 numbers in each. So if each had 3 numbers in it, then we would have allocated 3 times 5, which is 15 numbers. but it says that 16 were written on the board. So there's one more number. So these have already got 3 in them. So when we stick one more, well, one of the holes has then got to have at 4 in it. At least that, of course, because who's to say that necessarily all of those are going to have 3? They might not all have 3. So if that's the case that they don't already not have 3, then at least one of those holes has already got 4 in. All right, so it's kind of, you know, we're not necessarily looking at it exactly, but we can use that exactly one for our intuitive kind of thing. All right, so when we put the next one in, one left. That is shocking. So we've got one left. It's better. So when we put that in, at least 4 in one of the holes. Remember, see, it's the at least 4 in one hole. Could have 5, could have 6, but at least 4 is in one of them. All right. So at least 4 have the same. Therefore, at least 4. I forgot the least. Very important. At least 4 have same remainder. All right, and that leads to this here, like the generalised pigeonhole principle, as it's called. So if you've got m times n plus 1 objects placed into n holes, so this n here and this n here are the same, then some hole contains at least m plus 1 objects. So if you look in the example above, 5, the number of holes was n, so n was equal to 5. All right, and m plus 1 objects. So mn plus 1 objects, so the number of objects, so mn plus 1 was equal to 16, so mn was equal to 15, and because n's 5, so m is equal to 3. So m plus 1 equals 4 objects. So you can see that that applies to that example that we had above. Right, so 3 times 5, m times n, one more than that, which is 4, so at least 4. All right, so that's it for the pigeonhole principle. It takes a little bit of like thinking about what's going on. So it's more intuitive than looking at any specific thing, but you can do things like, say, for example, if you've got a room, and let's say you're in a room in a lecture or a conference or something, and say you have 500 people in it. You can confidently say that at least 2 of those people have the same birthday. All right? At least 2 of those 500 will have the same birthday. There may be more, but at least 2 of them. And you kind of think, how's that got to do with the pigeonhole principle? Well, it does, because how many days in the year, including the leap year, well, normal year is 365, but there are some people born on a leap year, so in that year there's 366. So 366 people could have a different birthday, but then once you start putting in those rest of people, they've got to have birthdays, the same birthdays as others. All right, so that's the kind of thing that the pigeonhole principle is used to show. All right, I'll stop me waffling on there. And as there's plenty of stuff on YouTube about it, and that if you're really interested in that, same with Pascal's triangle, what we did. So if you're interested, you can go and get your good old maths nerd on, which is a good thing, and you can watch some pretty cool stuff. All right, and as always, have fun.